Torsional pendulum. This is an experiment to find out moment of inertia of a regular object and also to determine the rigidity modulus of the material of suspended wire. Torsional pendulum was first developed by Robert Leslie in 1793. It is an experimental setup consisting of a disc-like mass suspended from a thin wire. When the mass is twisted about the axis of the wire exerts a torque on the mass tending to rotate it back to its original position. If twist is released, the mass will execute periodic oscillations about the axis of suspension perpendicular to its plane. These oscillations are called the torsional oscillations. In linear kinetics, the inertia means the resistance of the body to acceleration and mass is the measure of inertia. Equivalently, in rotational kinetics, moment of inertia is the resistance of the body to its rotational acceleration and it is the measure of amount of torque required for any change in angular momentum of the body. It depends on mass distribution and axis of suspension of the body. Unit of moment of inertia is kg meter square. The moment of inertia of rotating flywheel is used in machine to resist variations in the applied torque to smooth its rotational output. The moment of inertia of the aeroplane about its longitudinal, horizontal and vertical axis determines how steering force on the control surfaces of its wings, elevators and tail will affect the plane in rolling, pitching and yawing. Here in this experiment, the couple acting on the free end of the wire is called shearing stress and angular deformation produced at the fixed end of the wire is called shearing strain. Rigidity modulus is defined as the ratio of shearing stress to shearing strain within elastic limit. Hence, one can also find the rigidity modulus or shear modulus using this experimental setup. Let us look at the procedure of doing this experiment. Regular objects such as mass of the rectangular object, mass of the circular object and breadth of the rectangular object, length of the rectangular object, diameter of the circular object are measured and the observations are tabulated. So here length of the given rectangular object is 15.2 centimeter. Breadth of the object is 10 centimeter. Now, the radius of the rectangular disc is 50.4 centimeter. All these observations are tabulated. Then, the moment of inertia of regular objects about the defined axis are calculated using the appropriate formula. Now, the regular shaped objects are suspended at the free end of the given experimental wire to form torsional pendulum. So, let us start with the rectangular object. Suspend the object at the free end. So, now this setup is called as torsional pendulum. Then the object is said to execute torsional oscillations. Fix the reference so as to note the time period for one oscillation. So, execute torsional oscillation. So, just give a small twist in the wire and release the object slowly, very gently so that object executes Now start the timer keeping one reference point. Count number of oscillations as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop the timer. Note the corresponding time taken for 10 oscillations. Tabulate. Repeat the trial for 3 times. One, two, 3, 4, 5. Now change the axis of suspension so that it passes through the center of the body perpendicular to its breadth. Again, repeat the experiment by suspending it. Note period of oscillation for this axis of suspension, taking your reference as one corner of the rectangular slab. Start your timer. 2, 6, 7, 8, 9, 10. Repeat the trial for 3 times. Now suspend the object in the other direction, wherein the axis of suspension will pass through its center but perpendicular to its length. Reset the timer and again note the time period for this particular setup. You can give a small twist, execute torsional oscillations. Start the timer, taking one reference. 2, 3, 4, 5, 6, 7, 8, 9, 10. So repeat in this position 3 times. Tabulate the corresponding readings in the tabular column. Repeat the experiment with the other regular object which is circular in nature. First, the axis of suspension passing through its center perpendicular to the plane of the object. Execute torsional oscillation. Start your timer with respect to the reference point. Count number of oscillations: 10, 2, 1, 2, 3, 8, 9 and 10. Record the readings. Repeat the trial with the 3 times. Now suspend the object so that the axis of suspension passes through the center but along the diameter. Reset your timer. Execute torsional oscillations. Reset your timer. Execute torsional oscillations. Start your timer. Count number of oscillations: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Repeat the trial with the same setup 3 times. Now suspend the irregular object. Any axis of suspension can be. So let me choose axis perpendicular to its, taking one corner as the reference. I'll start the timer. Count the number of oscillations: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Record the reading. Repeat this trial for 3 times. So there is a definite relation between the time period and moment of inertia of the object. So irrespective of this shape and size of the object, the ratio of I by t square remains constant, and this is the principle behind the experiment which is used to find out the moment of inertia of irregular object by knowing the I by t square ratio of regular object. Now, length of the wire used in the experimental setup is noted, also noted, and it is 15.5 centimeter in this case. Now, all the readings corresponding to 10 oscillations are noted. All the readings are tabulated in the tabular column. The trial 1, trial 2, trial 3 readings for every regular objects, rectangular and circular, as well as irregular, for various axes of suspensions are recorded, and time period is evaluated, and t square is also tabulated. Now, a graph is plotted between moment of inertia and square of the time period of regular objects, which shows a straight line which reveals that I, moment of inertia of a regular object, is always proportional to square of the time period of corresponding object. Slope is evaluated, which gives I by t square ratio. Now, radius of the wire is determined using screw gauge. So, before that, the least count of the screw gauge is evaluated using the relation pitch by number of head scale divisions. So, this screw gauge is an instrument which works on the principle of pitch. So, you have a pitch scale graduated in millimeter. The maximum graduation is 25 millimeter and minimum graduation is 1 millimeter on the pitch scale. And you have 100 divisions, equal divisions on the head scale, which rotates on the pitch scale. So, you should always operate this screw gauge using the shaft or using the ratchet part of the screw gauge. When you close the two jaws of the screw gauge, the pitch line should coincide with the zero of the head scale, but in many of the cases it is not so. Here in this particular case, it is observed that the 0 is above by 2 divisions, that means it is coinciding with 98. So, for whatever the measurement that I do, I should add 2 divisions. So, that is my 0 correction. So, let us fix the wire between the two jaws and note the corresponding pitch scale reading and head scale readings. Pitch scale reading is here 0, head scale reading is 56. So, I need to add 2 for this particular reading so that my 0 correction is done. So, 56 plus 2, 58 is the head scale division. And least count of the instrument is pitch by number of head scale division. Pitch is nothing but the minimum division on the pitch scale, that is 1 millimeter by 100 divisions, turns out to be 0.01 millimeter or 0.001 centimeter. So, by noting the readings at 3 different positions of the wire, tabulate the corresponding readings and evaluate the radius of the wire. The mean value of radius is noted from the table, and calculations of moment of inertia of irregular object is found using the relation Ix is equal to Tx square into slope, where Tx is time period of the irregular object. Slope is obtained from the graph and the product will give you the moment of inertia of irregular object. And also the rigidity modulus of the wire used for the suspension is evaluated using the relation eta is equal to 8 pi L by r to the power of 4 into slope. where L is length of the wire already recorded, radius of the wire so determined. So, substituting all the values and slope taken from the graph multiplied by the 8 pi L times r to the power of 4 will give you the rigidity modulus of this wire. So, the wire is being made of steel material, and the value of rigidity modulus here in this case ranges between 7 to 8 into 10 to the power of 10 newtons per meter square. So, the results of the experiments, depending on the size and shape of the object, irregular object, the moment of inertia will be obtained. Rigidity modulus comes around 7 to 8 Newton per meter, 7 to 8 into 10 to the power of 10 Newton per meter square, as the material of the wire is steel. The probable viva questions for this experiment is as listed.